Welcome to 52nd lecture in the course of Industrial Engineering and Operations Research. We are discussing an important topic of operations research, that is called queuing theory. It can also be called waiting line models. Basically, here we study the behavior of the queues, performance of the queues, how many counters should be opened, practical things like that. If you are purchasing the tickets at some booking counter, naturally you have to stand in the queue. There may be several counters, they may run parallel, and there may be many people, so you may have to take decision whether more counters should be opened or not opened, how much time is the waiting time. These things are analyzed properly. However, here we use probability because behavior of the customers and how much time it will take for servicing is not known properly. So, we can actually say it in terms of the probability only. We can do that in terms of the probability. So, therefore, in the previous lecture I gave a good introduction about queuing theory, various type of queues, and in this lecture we will go little bit more mathematical. Okay. In the last lecture I also told about exponential inter-arrival probability distribution function. PDF was in the form of exponential, and according to that they arrive. And I also showed some mathematics, but here we will study little bit in depth. So, first I want to discuss sometimes we take pure birth model. So, how the births take place, this model can be used. Population increases over time due to births. Suppose it can be example that in a city children are getting born, but this may be of any other situation also where the birth model is employed. Maybe that if you are having very large machine shop where thousands of machines are there, and machines get, let us say that these machines, and maybe that they may be arriving also, people may be purchasing also the machines. So, we can apply there the birth model. You have to see that situation, that where we can apply the birth model and where you can apply the death model. So, here in pure birth model, population increases over time due to birth, it keeps on increasing, no reduction in the population, only arrival occurs. So, we only study arrival behavior. Example is bacterial growth in nutrient rich environment. Suppose how the bacteria grows, creation of birth certificates for newly born babies. So, babies keep born only, and birth certificate issuing office only issues the birth certificate. Exponential distribution is used to describe the inter-arrival time in pure birth model. So, last time I told you that the probability distribution was this one, Ft is equal to lambda e to the power minus lambda t. Of course, t time should be greater than 0 only. There is no point that time is less than 0. So, time should be greater than 0, and you can say that, of course, you can plot it, okay, this one, and this here it becomes Ft, and this is, so at t is equal to 0, you can maybe include 0 point also. So, this value is lambda, and then finally it will exponential decay at t is equal to infinity. This is the thing. So, this is basically time, and this is Ft. So, it is a probability density function. It is not probability, it is probability density function. And what is the unit of the lambda? Lambda is in per second, per unit time, okay, per second or per day, whatever that, per unit time. So, that is why lambda into t will be non-dimensional, and then only you can take its exponential. So, it will be e minus lambda t. So it is a basically a probability density function. Probability density function doesn't tell that what is the probability. If you really want to know the probability, then you have to do integration. You can find out the area under the curve. If I want to find out that what is the probability that there will be arrival from, say, let us say this time is 0 and this time is capital T, then 0 to capital T you take the area under the curve and that will be the probability. So density function is basically a type of say per unit type of thing. So therefore one should not confuse with probability density function and probability. Similarly, if you want to say that this is T and this may be, let us say I put it T1 and I put T2, and if you want to say that between T1 to T2 what will be the probability that you know that there will be inter-arrival time will be between this and this, then naturally that you can take the area under the curve. Okay. So this type of thing can be known that this one. So we told that exponential distribution and this is arrival. So mean time, you can say average time of arrival per unit time is this much. Suppose 50 people are arriving per hour, then of course you can express in the form of probability distribution function. So exponential distribution is used to describe the inter-arrival time in pure birth model. Okay. So now suppose we say P0 is the probability of no arrivals during a period of time t. So that means during some period you went somewhere. Okay. No need to know the previous time history, you just went at, say, let us say that 10 o'clock, and you want to say that within next half an hour, that means 10:30, whether there is no arrival, this you want to record. What is the probability that it will be? There will be no arrival in 30 minutes. So if the inter-arrival time is exponential, like if that behavior is like that, and the arrival rate is lambda customers per unit time, then P0T will be what? P inter-arrival time is greater or equal to T. So I am telling that it is greater or equal to T. Okay, that means we can say P greater or equal to T, and this will be equal to 1 minus P inter-arrival time is smaller or equal to T. So that is the probability if you want to know that. Okay. So probability that inter-arrival time is smaller or equal to T, that means between 0 to T you can integrate that thing and you can get. Now what happens that, okay, something that here more precisely, suppose I have written P inter-arrival time greater than T, then I should have written P inter-arrival time less than T. Okay, fine. But you know that just at one point, okay, this may not be that serious thing, because if you want to find out exactly at T what is the probability, so that probability is of course 0. So probability that inter-arrival time is greater or equal to T, it can be said like this. Okay, you can say from here to here. Okay, you can say from here to here, and probability that inter-arrival time is less than this can be area between this to this. Okay, so area we can say from 0 to T, like that loosely we can say. Now T is counted in both, but this is just a boundary, so it doesn't matter. Okay, now what happens that, so let us see that how you can find out the area. Suppose this is time T and this is, I am indicating this also by T only. Let us say that variable time is T, or I can say, okay, let variable time be T only, and you can I can use that same thing notation for this also, and I can say this is Ft. So this is Ft. So suppose you want to find out area between this one 0 to this one inter-arrival. So if you just integrate 0 to T lambda e to the power minus lambda T dt, okay, this will give area from 0 to T. So this becomes lambda e to the power minus lambda T divided by minus lambda, and this limit has become 0 to t. Okay. So, if I do like that, this becomes minus e minus lambda t to, and limits are 0 to t. So, what happens that if I put it like that, if I put that t, so I get 1 minus lambda t, and this if I put t is equal to 0, I get 1. So, but it is on minus sign, so minus minus becomes plus. So, it becomes 1 minus e to the power minus lambda t. So, that means probability that inter-arrival time will be less than t, that is actually 1 minus e minus lambda t. Therefore, probability that there will not be any arrival in time period t is 1 minus this much quantity, that means e minus lambda t. So, this gives you that the probability that inter-arrival time is only more than t. So, therefore, there is no arrival till time t. Okay. If somebody has come exactly at t, that is the border, that thing, will you consider that in this case or that thing? That question is mathematically little bit, you know, that very say tricky. Suppose I say that in 30 minutes. So, just as 30, so it depends whether you consider 30 plus or 30 minus. So, it is just border case, but since it is a continuous thing, so it does not matter that, okay, you can say that probability that inter-arrival time is this one. So, what happens that, what I mean to say that if I put here P0 t, suppose I put t is equal to 30 minute and lambda rate is known in terms of minute only. Whatever unit I put for t, the same type of unit should be used in lambda in per minute sense. So, that lambda into t becomes non-dimensional. You should never do that this mistake. Suppose I might have given time in minute, but lambda is per hour. So, you have convert per hour to minute or minute to hour, so that lambda into t should be non-dimensional, like that you have to do that. So, suppose t is equal to 30 minute, so we can find out that probability that there is no arrival during a period of 30, it can be found by e minus lambda t. Okay. Maybe that somebody just reached at 30, then you can say that he reached at 30.00000000, maybe one thing, so it will not be counted. Or if you say this is this thing, so it is, that means probability that there will be, even if it means little bit more, so then maybe we can say that, okay, that probability does not increase that much actually also. No? So, this is also very interesting, that suppose you say I can tell you that what is the probability that arrival will occur between 0 to 30 minute, because I can find out the area. But if you say that tell me exactly what is the probability that precisely at 30 minute that person will come. So, this I can do if the events are discrete. In continuous time I cannot tell, that means the answer will be 0. Probability that 30 minute is also 0, probability that he will exactly comes 29 is also 0. That means exact thing is the why, because area of line is 0. So, at 30 minute area will be 0. So, this is the thing you have to understand, and this is anyway. So, here it shows that probability that no arrival in time t is e minus lambda t. If I put probability that there is no arrival in 0 time, it is e minus 0, that means 1. So, of course, that in 0 time here no arrival will take place, so it has to be 1. So, mathematically it is consistent. Probability that there is no arrival in infinite time, put t is equal to infinite, it becomes 0. So, that means that probability is 0, because of course, in infinite time anything can happen. So, at least one person will come. So, that probability is 0. So, it is, and probability, this probability keeps exponentially decaying from 0 to 1, okay, sorry 1 to 0. So, like that. Why it keeps decaying 1 to 0? Because you know that probability as time increases, then chances that other person will join increases. So, probability of no arrival should keep on increasing. Okay. So, now what happens? Let us see it from other angle, in which we use Poisson distribution. Suppose I indicate P and T by probability of n arrivals during a period of time t. Okay. That means right now I was asking that probability of no arrival, that is okay. Now I am telling that there should be n arrivals. I have given some time to you. So how do you find out? For that purpose you use Poisson distribution here in the pure birth model. Exponential and Poisson distribution are mathematically related, but I am not going to in that much derivation. I am just explaining. Please keep in mind, if n is the number of arrivals during time period t, suppose n is the number of arrivals during time period t with mean of 1 by lambda. Okay. That means arrival rate is lambda. Arrival rate is lambda, therefore mean time between arrival will be 1 by lambda. If this data is given, then P and T is obtained as lambda t to the power n e minus lambda t factorial n, and where n can be 0, 1, 2, 3 and it can go up to infinity. So probability that 1 lakh people will be present in the system, that also can be calculated, but of course it will be very small number, because you can know that how much 1 lakh exponent factorial is that. In the bottom there is a factorial also. So that is why naturally that probability will keep decreasing, and sometimes but otherwise between 0, 1, 2 etc. it may be different. Okay, it may increase, decrease, but you know naturally that if n becomes very large, then this becomes of course almost 0, but we put that this formula. So let us check this formula. Suppose P and T. Suppose I want to say probability that there is 0 arrival in time t, that becomes P0 t lambda t. So lambda t to the power 0 is 1, and e minus lambda t and factorial 0 is 1 only. So it came same answer that you saw in exponential distribution. So P0t is of course e minus lambda t. But if I want to find out P1t, that probability that in that time period there will be one customer at least. So this is lambda t and e minus lambda t, because factorial 1 is this one. So therefore factorial 1 is 1 only. So therefore P1t is equal to lambda t e minus lambda t, P2t is equal to lambda t square e minus lambda t. Like that this type of thing will be there. Okay. So even you can say that if you sum that thing, probability that in some certain time there will be 0 people, there will be 1 person P1t, there will be 2 person P2t, and there will be 3 person P3t, and plus like that, it will go up to infinity, because that. So all the probabilities if you add, this will be what, e minus lambda t first term, another one will be lambda t by factorial 1 e minus lambda t plus lambda t square divided by factorial 2 e minus lambda t plus lambda t cube divided by factorial 3 e minus lambda t. Like that it will go. So I can take e minus lambda t common. Okay, let me erase this and write it here nicely for you. Okay, I am writing in inclined way. So suppose here I write like this. Suppose I say total probability. So that means probability that there will be 0 or 1 or 2 up to infinity. So I can take e minus lambda t common, and I can take in the bracket 1 plus, I can say lambda t by factorial 1 plus lambda t square by factorial 2 plus lambda t factorial cube by factorial 3. Like that it will go. So if you can see, you can recognize this series 1 plus lambda t. So it is compare 1 plus x by factorial 1, 1 plus x square by factorial 2. So this is basically e to the power lambda t. So therefore e minus lambda t multiplied by e lambda t is e to the power 0 is equal to 1. So naturally it has to come 1. That means there will be one thing, either there will be 0 customer in the system, or there will be 1, or there will be 2, or there will be infinity. So, this is how. So, you remember this formula also. This is also very useful about the Poisson distribution. Let us see that one example. A customer support center has a phone line where new calls are issued at the rate of 1 call every 4 minutes. The time between phone calls follows an exponential distribution. Time between phone calls follows an exponential distribution. Calculate the average number of calls per year and probability that the next call arrives within 2 minutes, probability that the next call arrives after 5 minutes. Let us do this problem. Okay, just see. So, arrival time between calls is 4 minutes. So, therefore, it is very simple. Calls per day will be 24 into 60. Minutes are there, divided by 4, that means 360. So, 360 calls will be per day. Okay. Question was what? That average number of calls per year. So, I have completed calls per day. Now, you multiply it further by 360, then you can find out call per year. Okay. I have not done this. Okay. You just do that 360 into 360 means if in a year you consider 360 days. Okay. So, that is what that you can do that. And now, other question was the probability that the next call arrives within 2 minutes. Somebody went and he wants to see that when the next call comes. So, given t is equal to 2 minutes, arrival rate is equal to lambda is equal to 1 by 4. So, that means arrival rate becomes, arrival rate was t is equal to arrival time was 4 minutes. So, arrival rate is 1 by 4, that means 0.25 calls per minute. So, probability that next call arrives within 2 minutes, that probability that time is smaller than t is basically 1 minus e minus lambda t. Okay. That we did that probability that t is smaller than t is, this is 1 minus e minus lambda t. So, therefore, this becomes 1 minus e minus 0.25 and is equal to that you put here, you see that lambda you have put 0.25 call per minute and multiplied by time is 2 minutes, minute cancels. So, this answer will be 0.39. Or you can say this thing, if you remember this formula always P0 t was e minus lambda t. So, first we can calculate that there is a no arrival up to time 2 minutes. So, you put lambda is equal to 0.25 and you put 2, and then opposite will be question which has been asked is opposite, that the probability that there will be one arrival within 2 minutes. Okay. So, that is. Now, the probability that the next call arrives after 5 minutes, if you want to find out after 5 minutes. So, that means within up to 5 minutes there is nothing. Okay. But after 5 minutes, what is the probability? So, probability that next call arrives after 5 minutes, p t greater than t, that is e minus lambda t, and this will be, that means it is same as there is no call up to 5 minutes. So, it will be e minus 0.25 and this is 0.287. So, chances of getting a call after 5 minutes is 28.7%. Chances of getting call before 5 minutes is much more. Okay. So, this is the thing. So, you have to understand the language very carefully, otherwise in probability questions why students face difficulty, because they are not able to understand the language. Here it is saying next call arrives within 2 minutes. Okay. It can be 1.5 also, it can be 1.9 also, but here it is saying the probability that next call arrives after 5 minutes. It can be 6 minutes, it can be 7 minutes, it can be even 5.1 minute. Okay. So, this is how that now similarly there is a pure death model. This model is the opposite of the pure birth model. So, here the system loses member over time, but no new arrival occur. Examples are that in autumn season leaves are falling from a tree and you say that they are decreasing. Okay. People leaving a queue when the service counter closes permanently. Suppose in the service counter closes, then people start leaving, or maybe that after that some movie show is over, then one by one people start leaving, or maybe other situation also when the talk, a boring lecture is going on in some auditorium, and then gradually the people start moving, the speaker will keep on speaking, okay, till even one person is there, but the slowly people are leaving. So that is, then battery power devices gradually shutting down as batteries die. Even you can say machines in some facility are gradually getting phased out. Models decay, failure or departure, these type of things, something, some decay type thing is there. Here also we use the exponential distribution, in exponential fashion they go. So in this model, the system starts with n number of customers. In the pure birth model, it started with 0 and it keeps on increasing, but here n customers are at time t is equal to 0 and no arrivals are allowed. Departure occur at the rate of mu customers per unit time. This is average. And so probability P and T of n customers remaining after t time units is how much? P and T is actually mu t to the power capital N, means capital N is the number of customers which was at time t is equal to 0, and this small n is that what we are finding, n customers at after time t unit. So n minus n e minus mu t and divided by factorial n minus n, this one factorial, and n is equal to 1, 2, 3 n, it will not go up to infinity. So P0 t is actually that basically you can say what probability that there will be 0 people at some time t, 1 minus sigma n is equal to 1 to n p and t. Okay. So you can find out by that formula. So this also you can note down. Now I am telling that about general Poisson queuing model, okay, where basically arrival time is exponential, or you can say Poisson behavior in queue. This model assumes that both arrival and departure are state dependent, general model. It means it is dependent on the number of customers in the service facility. For example, the number of machine breakdown decreases as the number of broken machine increases. Okay. So there can be like that. This is because only working machines can generate new breakdown. So I am assuming that in a special case, suppose n is the number of customers in the system, that means in queue plus in service, and lambda n is arrival rate given there are n customers in the system, mu n is the departure rate given n customers in the system, and p n is equal to steady state probability of n customers in the system. So p n is obtained as a function of lambda n and mu n. Probability is used to determine the system's measure of performance, such as average queue length, average waiting time, and average utilization of the facility. Average utilization of the facility is what? Proportion of time the service facility like a machine or server is busy serving customer, that is called this one. So average utilization of facility is arrival rate by service rate for single server system, that it is simple that utilization. Suppose my service rate is I can service 20 people in 1 hour, but only 10 are arriving. So naturally my utilization will be 50%, 10 by 20. But suppose all 20 is only coming, then utilization will be 100. Okay. So this ratio is arrival rate by service rate. If there is only one queue, we talk. Anyway, let us talk about general Poisson queuing model. So probabilities are determined by using transition rate diagram. It is something transition diagram. Here suppose we show the system. Suppose there are 0 people in the system, then one arrival occurs lambda 0 at a rate of lambda 0, then it becomes 1. And from 1 state to you can get 0 state by servicing one customer at the rate of mu 1. And similarly 1 to 2 you can go lambda 1 is the arrival rate, and mu 2 you can do service, you can go to previous state, then 2 to 3 you can go, 3 to 2 you can come back, like that. This type of diagram is there. So n is equal to number of customers in the system in queue plus in service, lambda n is arrival rate given n customers in the system, that state dependent lambda, mu n is equal to departure rate given n customers in the system. So under steady state conditions for n greater 0, the expected rate of flow into and out of state n must be equal, because steady state is there. So state can be changed to n minus 1 and n plus 1. So expected rate of flow into state n is lambda n minus 1 into Pn minus 1 plus mu n minus 1 into Pn plus 1, because lambda n minus 1 is the rate and Pn minus 1 means actually the system was at n minus 1 state, then it went to state n by arrival. So this becomes the product of this. Similarly, mu n minus 1 into Pn plus 1, same type of thing is here, becomes like this, and this becomes this one. So this becomes suppose the state was Pn plus 1 and then this is mu n plus 1. So it should be, I think, mu n plus 1. Okay. So this is like that, and expected rate of flow out of state n is lambda n plus mu n into Pn. Okay, because it is going, that means this is the one state of system going out of. Okay, so this is state of out of state. So mu n, this is mu n and this is lambda n. Okay, so this is mu n plus 1 and this is right. So the both sides you the equations is obtained as lambda n minus 1, this is mu n plus 1 and is equal to, you equate that n is equal to 1, 2, 3 and you solve this difference equation. Equation with n is equal to 0, that means suppose you are already in state this one. So you will leave the state at probability P0 into lambda 0, this becomes this one and mu 1 into P1. So for n is equal to 1, the equation is this much, and you can actually get, you solve that, then you can solve these difference equation and you can get Pn is equal to this formula. So this formula you can remember, n is equal to 1, 2, 3 and the value of P is determined by summation up to infinity, n is equal to 0 to infinity, Pn is equal to 1. So let us do an example. Okay. Lambda 0 is equal to 5 customers per hour, lambda 1 is 4 customers per hour, lambda 2 is equal to 3 customers per hour. No arrival take place if there are 3 or more customers in the system. Maybe by seeing the 3 customers, the people will run away. Service rates, mu 1 is equal to 1 customer per hour, mu 2 is equal to 4 customers per hour, mu 3 is equal to 10 customers per hour. Find out the probability that there will be no customer in the system. Suppose there are more customers, then you know service counters are open more, that is why this situation is happening. So you put Pn is equal to that formula lambda n minus 1 and you put P1 is equal to lambda 0 by mu n P0. So P1 is equal to 5, 0, P2 is equal to 5 pi P0, P3 is equal to this much, that means 1.5 P0 and P4, P5 will be obviously 0 because lambda 4 is 0, lambda 5 is 0 and this one. So if you put that thing, now you do summation, sigma n is equal to 0 to Pn, 1 is equal to P0 plus P1. So P0 plus 5 P0, 5 P0, 1.5 P0. Sometimes you may have to do infinite addition also, but here it was other things were 0. So that is why that this is coming. So this equal to 12.5, P0 is equal to 1 and P0 is equal to, therefore P0 is equal to 0.08. So I should say P0 is equal to 0.08. Okay. So this is what it implies, that P0 is equal to. So this is how you can find out P0. Special cases, suppose you take a special case. So arrival and service rate constant, then Pn will become lambda mu n P0 and this will become lambda by mu can be indicated by rho, that is utilization factor, and this is the thing. So if you can do the summation up to infinity, P0 plus rho square is equal to 1 and therefore P0 is equal to 1 minus rho. If you want to find out what is the length of the system, you can say n is equal to 0 to infinity and you can say corresponding, suppose there are n customers and corresponding probability. So n into this thing, that gives mathematical expectation. You sum it from 0 to infinity, and this summation I have done. You can do in a different way, but I just have written it as a differentiation of this quantity and this becomes basically rho divided by 1 minus rho. So, length of the system has also come. So, let us do one example. On an average, 10 patients keep waiting at the clinic of a doctor. Doctor spends 10 minutes for seeing a patient. On an average, 19 patients remain in the system, that means Q plus consultation in 2 hours. In 2 hours, how much time doctor is busy? What is the arrival rate of customers? What is the average waiting time? Assume Poisson arrival and negative exponential service time. This type of things can be their question. So, average number of patients waiting in the queue, LQ is equal to 10. Average number of patients in the system, Q plus consultation. Suppose I just have written 19 patients, okay. Service time mu is equal to 10 minutes per patient. If we say that, suppose this one, R 1 by 10 patients per minute, R 6 patients per hour. So, if I want to say that, we know L is equal to rho by 1 minus rho, okay. That formula was given system. So, rho is equal to L divided by 1 plus rho, and that becomes 0.95. So, rho is the must be the average utilization of the facility, that is 0.95, and busy time of the doctor is equal to suppose 2. So, 0.95 into 2 is equal to 1.9 hour, and this is equal to 1.1, and using P is equal to lambda by mu. So, here mu is actually known, suppose it is this one. So, therefore, we can say mu is equal to 6 patients per hour. So, lambda is equal to becomes 5.7 patients per hour, and average waiting time WQ, okay. So, this becomes this one, but there is a this one that okay, we will discuss more in detail about that. If there is a single server, okay, then of course in that case this type of thing that LQ has been given 10, this data is actually may not be correct, because in that LS is equal to will be LQ plus rho. That type of answer should be there. So, there has to be 10.95 type of thing, because you cannot say there is a single server. In the worst case, LS can be, means in the maximum case, LS can be 1 more than Q, okay, LQ plus 1. But in the system, there will be this one. So, therefore, this data has to be that properly this one seen, okay. So, sometimes even if in the exam, if anything comes, don't close your eye, analyze it properly, okay. If you know that this is the thing, so on an average 19, if you have said that in the LS, in the system, if there are 19 patients, okay, that means there cannot be 10 patients waiting in the queue, because that doctor fellow, if he is alone, of course, he is not seeing 9 patients at one time, okay, he sees only 1 patient. If there are parallel channels, then it is possible. So, about multi-channel queuing system, we will talk later, okay. Thank you very much for your attention. Okay.